If gasoline can power everything from a lawnmower to an Italian supercar, why does it fall short when it comes to trucks? Most people believe it's just a matter of price at the pump, but that's only the tip of a steel and fire iceberg. The real answer is a century-long war between two combustion philosophies, where the battlefield is a space no bigger than a coffee cup, the inside of a cylinder. Imagine you have to convince 40 tons of steel and cargo to abandon their rest and start rolling. That's not a job for a gasoline engine, no matter how powerful. It requires a brutal push that the spark simply can't deliver. Almost everything you touch right now came to you because a machine accomplished that monumental feat, and it did so using a secret that gasoline completely ignores. In this video, we're going to break down the technical and physical reasons why a gasoline truck would be a total disaster. Stick around until the end, because I'll reveal the fact about compression ratio that explains why a diesel engine can last 1,000,000 kilometers while a gasoline engine would explode trying to do the same job. Because when the mandate is brute force and infinite endurance, there is only one king, and that crown is not forged with spark plugs. Moving the immovable. It all starts with a fundamental law, not written in engineering books but in the harsh reality of every loading dock, every open-pit mine, every infrastructure project. The raison d'être of a truck, its purest essence, is not speed. Nor is it elegance, luxury, or dizzying acceleration. Its primary mandate, its ironclad oath, is to generate force. A force so tangible you can almost touch it, a force measured in the ability to overcome the inertia of masses that defy gravity and common sense. Think of a dump truck leaving a quarry, its massive tires sunk into the gravel, its bed loaded with 60 tons of rock. At that moment, when the driver selects the gear and presses the accelerator, that vehicle is not asking for galloping horsepower. It is begging for torque. Torque is the true muscle of the industrial world, the mechanical equivalent of the tension in the tendons of an Olympic weightlifter in the second before the lift. It is the twisting force applied directly to the axle that converts the controlled explosion in the cylinders into a rotational thrust capable of turning those wheels, breaking the grip of the earth, and initiating the slow, majestic, and heavy advance of civilization. This is the first and most important filter through which any technology that aspires to power a truck must pass. It doesn't matter how refined, efficient, or advanced it is. If it can't generate mountains of torque at absurdly low revs from near idle, it can't even enter the fray. It is here, at this altar of brute force, that the gasoline engine, the undisputed king of light roads, encounters its first and most decisive wall. Because generating that kind of force is not simply a matter of making a bigger engine. It's a matter of principles, of chemistry, of pure and simple physics. It's a battle that is won or lost in the internal geometry and controlled violence of the chamber where fuel is converted into motion. The battle inside the cylinder, compression versus detonation. To understand why diesel reigns supreme here, we must enter that cylindrical battlefield. Forget for a moment about makes and models. Think of the cylinder as a vertical cannon. At its base, the piston, a polished metal plunger, prepares for its race. The process for both engines shares a basic choreography. Admit air, compress it, inject fuel, cause combustion that expands the gases and pushes the piston down, generating work. But the devil, and the key to everything, is in the details of how that combustion is caused. In the gasoline engine, air and a fine vapor of gasoline are mixed outside the cylinder or in the intake. This homogeneous mixture is sucked in and then compressed by the piston on its upward stroke. However, there is a limit, a point of no return. If this mixture of air and gasoline is compressed too much, it heats up so much that it ignites on its own, uncontrollably and prematurely. This is detonation or knocking, a destructive metallic pounding that hammers the pistons and connecting rods. To avoid this, gasoline engines use a moderate compression ratio, typically between 8:1 and 12:1. Then, at the precise moment of maximum compression, an electric spark from the spark plug fires, initiating a controlled flame that sweeps through the chamber. It is a command-driven ignition system, precise but delicate. The diesel engine, on the other hand, plays a rougher and fundamentally different game. Only pure air enters the cylinder. The piston rises and compresses it with a ferocity that would make a gasoline engine pale in comparison. Compression ratios here range from 14:1 to 25:1. This air, being compressed so violently, heats itself to extreme temperatures, well above the auto-ignition point of diesel. It is then, at the critical moment of maximum compression, that the injector sprays the diesel fuel directly into that atmosphere of super-hot, super-pressurized air. The fuel does not need a spark. It finds such a hostile environment that it simply explodes on contact, almost instantly and at multiple points at once. This is compression ignition. The battle, therefore, is defined as follows. Gasoline requires low compression and an external ignition source to prevent self-destruction. Diesel requires brutally high compression, which is just what it needs to create its own ignition. And it is in this abysmal difference in working pressure that the first great advantage of diesel for heavy-duty work is born, because that stratospheric compression is directly linked to the generation of force. How torque is forged. Now let's connect the dots between that compression explosion and the torque that moves mountains. The key lies in what engineers call the piston's stroke. Imagine the cylinder again. The distance the piston travels from its lowest point to its highest point is its stroke. Engines can be short stroke or long stroke. A short stroke engine, typical in many high-performance gasoline engines, allows for high revs quickly, which is ideal for generating a lot of power across a wide range of RPMs. But to build torque, especially the low, massive torque a truck needs, you want the opposite, a long stroke. Think of a wrench. If you want to loosen a very tight nut, you don't squeeze the wrench near the head. You take the end of the handle as far away as you can. You apply the same force, but by increasing the lever arm, you multiply the torque. A long-stroke piston works in a similar way. With a longer travel from top dead center to bottom dead center, the lever arm connecting the piston to the crankshaft is more effective. When the diesel mixture ignites and expands violently, it pushes the piston head. In a long-stroke engine, that thrust has more time and more linear distance to act on the connecting rod and therefore to turn the crankshaft with more torque. It is a slower, deeper and more forceful stroke. Each explosion is like the slow, powerful hammer blow of a blacksmith, not the rapid tapping of a jackhammer. This long-stroke design is intrinsic to the high-compression diesel philosophy. You need that space to compress the air sufficiently, and when you have it, you get the ideal lever arm for torque as a bonus. A gasoline engine that attempted an equally long stroke to seek that torque would once again run into the wall of premature detonation. It cannot compress the mixture enough to justify that geometry without self-destructing. Thus, diesel, by its very nature of compression ignition, is forced into a design that is optimal for generating the currency of the weight realm. The Newton meter of torque, available almost from the first beat of the engine. Low revs versus high revs. This fundamental divorce in design results in a difference in character as profound as that between a draft ox and a thoroughbred. It is the distinction between low revs and high revs, and it completely defines the personality of each machine in service. The heavy-duty diesel engine is a slow-turning animal. It generates its maximum torque, that overwhelming rotational thrust, often between 1,200 and 1,500 revolutions per minute. Its useful power zone, where it works efficiently and powerfully, rarely exceeds 2,200 revolutions per minute. Think about that. At 1/3 to 1/2 the RPM range at which a gasoline car engine is just entering its comfort zone, the diesel is already delivering its full power. This is not a flaw, it is a virtue purposefully carved out for the task. A truck doesn't need to accelerate from 0 to 60 miles per hour in 5 seconds. It needs to start moving its load from a standstill without strangling the engine. It needs to be able to maintain speed when encountering a slope in the road by simply pressing the accelerator a little harder, without having to downshift 3 gears and rev the engine to 6,000 RPM. Operating at lower revs drastically reduces internal friction, component wear, and overall stress. It is a sustainable, martial, constant pace of work. A gasoline engine, on the other hand, builds its power by revving up the tachometer. Its maximum torque usually reaches a much higher RPM, perhaps between 3,500 and 5,000 RPM. To move a heavy load, it would have to stay in that high range constantly, revving fast, consuming fuel voraciously, and subjecting its components to extreme cyclic stress. It would be like asking a sprinter to run a marathon at top speed. It's simply unsustainable. The character of diesel is one of patience and constant power. The character of gasoline in this context is one of urgency and peak effort. And on the highway, where trips are measured in hundreds of kilometers and hours behind the wheel in days, only one character is right for the job. Robustness by design. But generating this monumental force at slow speeds would not be feasible if the machine that does so wears out after 100,000 kilometers. This is where the diesel philosophy demonstrates its depth, building longevity from the ground up. A heavy-duty diesel engine is not a larger gasoline engine. It is an engineering beast forged under different premises. To withstand the cyclopean pressures of compression combustion, pressures that can be more than twice those of a gasoline engine, everything must be stronger, thicker, heavier. The engine block is not made of lightweight aluminum, but of thick cast iron, an immutable bastion against internal explosions. The cylinder heads are massive, bolted together with finger-thick bolts. The pistons are huge, often with a reinforced crown to withstand the heat and direct pressure of the flame. The connecting rods are forged steel bars that look like small beams. The crankshaft is a solid piece of steel, with a diameter that inspires respect, designed to absorb and transmit torques that would split a conventional engine in two. This excess of material, this deliberate oversizing, has a clear purpose: tolerance. These parts do not work at the limit of their strength. They work well below it. A high-performance gasoline engine is an elite athlete, sleek and optimized for maximum performance, but with a small margin for error. A truck diesel engine is a professional weightlifter with a massive bone and muscle structure that allows it to perform its daily feat, day after day, year after year, without injury. This robustness by design is what allows these engines not only to generate the necessary torque, but to do so over distances that seem like science fiction. It is the foundation that supports the promise of 1,000,000 kilometers, the legend of engines that outlive several chassis. It is the reason why, when the mandate is not just to push but to push forever, the heavy and slow diesel architecture becomes not a disadvantage, but the only possible guarantee. And yet this physical strength, this raw capacity, would be nothing more than an engineering curiosity if it did not translate into a universal language. The language of cost, efficiency, and cold business calculation. Because in the end, the laws of physics must yield to the laws of economics. The story we have followed so far, that of compression, torque, and robustness, could remain in the realm of theory in a fascinating treatise on mechanical engineering. But the world of freight transport is not driven by theories. It is literally driven by numbers. Ruthless, clear, and repetitive numbers that are written on expense sheets, fuel receipts, and companies' final balance sheets. It is here, in the cold light of commercial arithmetic, that the physical advantages of diesel translate into such overwhelming economic dominance that gasoline cannot even be considered as an alternative. Because understanding why trucks don't use gasoline requires leaving the workshop and going up to the fleet manager's office, where every decision is weighed in tons of savings or mountains of unnecessary expense. The density of power, more energy in every drop. To begin to unravel this economy, we must return to the origin, to the very essence of fuel. Not all flammable liquids are created equal. A gasoline molecule and a diesel molecule, although both are derived from petroleum, have different chemical structures. Gasoline is composed of lighter, shorter hydrocarbon chains. Diesel, on the other hand, is made up of longer, heavier chains. This molecular difference is not a trivial detail, it is the basis of everything. Those longer chains in diesel mean that in an identical volume, say a liter, there are more carbon and hydrogen atoms packed in. And since the energy in a fuel comes from breaking the bonds between those atoms during combustion, a higher density of atoms means a higher energy density. In practical, measurable terms, a liter of diesel contains, on average, about 10% more energy than a liter of gasoline. Think of it as the difference between light charcoal and compact coal. With the same weight or volume, the latter will burn longer and give off more heat. This is the cornerstone of diesel efficiency. The engine, through its brutal compression ratio and self-igniting combustion, is exceptionally good at extracting that intrinsic energy and converting it into useful work at the crankshaft. It's not just that the diesel engine is more thermally efficient, which it is, it's that the fuel it uses is, molecule for molecule, a more concentrated package of energy. From the moment the truck driver pays to fill the tank, he is buying more potential miles for each monetary unit, even before the engine starts running. This innate chemical advantage is the first and quietest multiplier in the economic equation of transportation. It is a gift from geology and refining that the diesel engine is uniquely equipped to take full advantage of, a perfect pairing of dense fuel and a machine designed to squeeze every last drop out of it. The endless journey, efficiency and the tyranny of distance. In the real world, this energy density translates into the king of long-distance road travel, fuel efficiency. And here, the differences cease to be modest percentages and become operational chasms. A modern heavy-duty diesel engine is a masterpiece of thermodynamic efficiency. By operating with excess air and extremely high compression, it manages to extract a greater portion of the chemical energy from the fuel compared to a gasoline engine, which loses more energy in the form of waste heat through the exhaust and cooling system. The result is a magic number for any transporter: kilometers per litre. While a hypothetical heavy-duty truck with a gigantic gasoline engine forced to work in its high-effort range could achieve, with luck, perhaps 2 kilometers per litre under ideal conditions, a modern diesel tractor-trailer can easily achieve 3 kilometers per litre, or even more. For a fleet, this figure is not a technical data point, it is a destination. Because the transportation business is defined by the tyranny of distance, routes are fixed, delivery deadlines are immutable, and kilometers accumulate with metronomic regularity. A long-haul truck in the United States or Europe can easily travel more than 150,000 kilometers per year. Imagine that journey, that endless succession of highways, nights at service stations, and repeating landscapes. Every litre of fuel saved on that endless journey is multiplied by 150,000. In concrete terms, diesel efficiency means fewer stops to refuel. Fewer stops mean less time the truck is stationary, with the engine off, not generating income. In logistics jargon, this means more time on the road. A truck is an asset that only makes money when it is moving. Every minute spent at a gas station, however necessary, is a minute of lost productivity. Diesel, by allowing fuel tanks that can exceed 1,500 kilometers on a single charge, reduces downtime, extends driving distances, and makes route planning more flexible and less urgent. Gasoline, with its lower energy density and lower thermodynamic efficiency in this type of application, would impose a much more frequent cadence of stops, a constant choreography of detours to gas stations, a fragmentation of the trip that would be the nightmare of any fleet dispatcher. On the endless highway, efficiency is not a virtue, it is a necessity for survival. A simulation on the road, the real cost of a what-if. Let's take this arithmetic to the realm of pure cash, to a simulation that any fleet owner does in their head, or better yet, in their spreadsheet. Let's use conservative numbers for our scenario. Let's assume a modest fleet of 10 tractor-trailers. Each one travels, as we mentioned, 150,000 kilometers per year. A modern diesel engine, professionally managed, can achieve an average fuel consumption of 3 kilometers per litre. This means that, in 1 year, each truck will consume 50,000 litres of fuel. Now let's take the price of diesel. It varies, of course, but for this exercise, let's use a base figure. The annual cost per truck is that volume multiplied by the price per litre. Now let's enter the realm of dangerous economic fiction. What would happen if those same trucks, doing the same job, on the same route, with the same load, were powered by gasoline engines of equivalent capacity? To move 40 tons, that gasoline engine would have to be huge, forced to work close to its limit, and its efficiency would plummet. It would be optimistic to assume that it would achieve 2 kilometers per litre. It would probably be less. With a consumption of 2 kilometers per litre, the same truck would consume 75,000 litres per year. 25,000 litres more than its diesel counterpart. Here comes the masterstroke, the fact that debunks the myth that gasoline is cheaper at the pump. Although in some markets the price per litre of gasoline may be 5 or 10% lower than that of diesel, the extra volume you need is so large, 33% more in our example, that the supposed advantage evaporates and is violently reversed. Multiply those extra 25,000 litres by the price of gasoline, and then multiply that by the 10 trucks in the fleet. The annual difference in the fuel bill becomes a 6, 7, or even 8-figure number, depending on the size of the operation. It's a black hole in the finances. It's the annual salary of several drivers, it's the maintenance of the entire fleet, it's the investment in new trailers, it's the company's profit margin. This what if is not an academic exercise. It's the calculation that keeps managers awake at night, and it's the reason why not a single trucking company would even consider gasoline for the bulk of its line work. The arithmetic is relentless, and its verdict is clear. Savings at the pump per litre are a mirage. The cost per kilometre travelled is the only truth that counts. The weight of gasoline, stolen payload. However, the fuel bill is only part of the economic story. There is another variable, often overlooked but equally critical, that relates to the most valuable asset a truck carries. Its payload. In road transport, every kilogram counts. There are strict legal limits on the total gross weight of the vehicle, which includes the weight of the empty truck, tare, the fuel, the driver and their belongings, and of course the merchandise. Any kilogram that is not merchandise is a kilogram of potential revenue left on the dock. And here, the lower energy density of gasoline plays another dirty trick. To achieve the same range as a diesel tank, you would need a larger gasoline tank or, more commonly, carry much more fuel volume for the same journey. But volume and weight go hand in hand. A litre of gasoline weighs less than a litre of diesel, but the difference is not enough to compensate for the huge extra amount you need. In our previous example, the gasoline truck would need to carry an additional 25,000 litres of fuel per year. On a long trip, that could translate into carrying hundreds of extra litres of weight in the tank at all times. That weight is not cargo. It is ballast. It is dead weight that the engine must drag along, which in turn further reduces efficiency in a vicious circle. Every kilo of extra gasoline in the tanks is a kilo of steel, grain, appliances, or raw materials that cannot be loaded. In a business where margins are measured in cents per ton-kilometre, stealing payload is a cardinal sin. Diesel, being more energy-dense, allows for tank designs that offer enormous range with relatively less impact on the vehicle's tare weight. It maximizes the proportion of total weight dedicated to what matters, the cargo the customer pays for. In the relentless balance of legal and economic weights and counterweights, gasoline not only costs more per kilometre, but also reduces the ability to generate revenue on each trip. It's a double financial penalty. Fewer trips to the mechanic, the economics of durability. Finally, we come to the last pillar of the diesel economy, one that transcends consumption and touches on the very lifespan of the machine, durability and its impact on operating costs. Let's recall the robustness by design from Chapter 1. Those cast iron blocks, those solid crankshafts, that low RPM operation, are not just for making a strong engine. They are for making an engine that almost never breaks down. And in the world of transportation, unscheduled downtime is the #1 enemy, even more feared than expensive refueling. A truck sitting in the shop is not just an asset that is not producing. It is an asset that generates expenses, the mechanic's labor, the cost of replacement parts, tow truck charges if it broke down on the road, and the intangible loss of customer confidence when their shipment is delayed. The heavy, slow diesel architecture is designed to minimize these events. The absence of an ignition system with spark plugs, wires, and coils eliminates an entire category of electrical failures common in gasoline engines. Lubrication of the diesel fuel in the injectors and pump is inherent in the system, while gasoline, which is a solvent, can present different problems. Low RPM operation exponentially reduces friction and fatigue wear on moving components. A well-maintained diesel engine can exceed 1 million kilometers before needing a major powertrain overhaul. A gasoline engine subjected to the constant stress of moving a heavy load would see its useful life reduced to a fraction of that distance, with major overhauls required every 300,000 or 400,000 kilometers. The cost of an engine rebuild or complete replacement is astronomical, capable of wiping out the benefits of many trips. In addition, preventive maintenance intervals on a diesel are typically longer, oil changes can be spaced further apart, fuel filters last longer, and the system overall requires less intervention. This translates into fewer repair bills, fewer days of scheduled downtime, and most importantly, absolute predictability. A fleet manager can plan maintenance months in advance, rotating trucks without affecting operations. The unpredictability of a less robust engine introduces chaos into logistics. Therefore, the economics of diesel durability are the economics of peace of mind. It is the assurance that your six-figure asset will keep rolling, day after day, reliably generating revenue. It is the knowledge that the total cost of ownership, spread over the hundreds of thousands of miles of the truck's life, will be lower. And in a business where reliability is as valuable as speed, this advantage is the final nail in the coffin of any consideration for gasoline in heavy transport. The choice, when all the numbers are on the table, is not even a choice. It is an inevitable conclusion dictated by the simplest and most powerful sum. More work, for less fuel, for longer, with fewer interruptions. That is the arithmetic that moves the world. the exception that proves the rule, where and why gasoline persists. Before exploring future threats, it is fair to acknowledge that diesel's dominance, while overwhelming, is not absolute. There are niches, specific corners of the market where the gasoline engine still fires up, precisely because the conditions that demand diesel are relaxed or reversed. The clearest example is found at the opposite end of the spectrum: light and medium-duty urban delivery trucks. Think of the vans that crisscross city streets, delivering packages, food or supplies. Their operating reality is the antonym of the open highway. Here, the routes are short, with constant stops. The cargo, while valuable, is rarely massive in weight. And the main enemy is not range, but agility, initial acquisition cost, and growing pressure for zero local emissions in urban centres. In this context, some of diesel's greatest virtues are diluted. A modern diesel engine, loaded with exhaust after-treatment systems such as AdBlue and particulate filters, suffers in stop-start cycles. These systems need constant temperature and flow to regenerate and function properly. A round trip to the city centre, full of traffic lights, can clog a filter, leading to costly maintenance and loss of efficiency. A turbocharged gasoline engine, which is lighter, has a more immediate response at low revs, and does not have the complex diesel emission treatment systems, may be a simpler and more agile option. Its purchase cost is lower, its maintenance is more familiar to general repair shops, and although its fuel consumption is higher, on short total journeys, the impact on the annual bill is manageable. In addition, it serves as a bridge to partial or total electrification, as the architecture of a light gasoline truck is more easily adapted to hybrid versions. Thus, in the concrete jungles where brute force and extreme autonomy give way to simplicity and adaptability to restrictive environments, gasoline finds its last stronghold. It's not that it challenges diesel on its own turf, it's that it survives in a radically different terrain, reminding us that in engineering, context is everything. The emissions trial, the weak point of the diesel king. If there is one front where diesel is genuinely on the defensive, it is on the battlefield of emissions. For decades, its efficiency was celebrated as an ecological virtue, as lower consumption meant less carbon dioxide released per ton transported. And in that regard, it remains hard to beat. But the war on pollution is being fought on multiple fronts, and it is on the fronts of nitrogen oxide and fine particulates that diesel has borne the brunt. High-temperature compression combustion is inherently prone to generating NOx, and the nature of the fuel, with its long carbon chains, produces soot. For years, these emissions were the accepted price of power and efficiency. But not anymore. Regulations such as Euro 6 in Europe and the EPA in the United States have raised the limits to levels that require almost miraculous engineering. The modern diesel engine is a tangle of containment systems. Exhaust gas recirculation to reduce combustion temperature and NOx, diesel particulate filters that physically trap soot for later incineration, and the SCR system that injects AdBlue into the exhaust to chemically convert NOx into harmless nitrogen and water. These systems have made it possible for a new diesel truck to emit a fraction of what it did 20 years ago. But the cost is high. Complexity skyrockets. Maintenance becomes more critical and specialized. Engine performance may be slightly affected, and the price of the vehicle increases significantly. This is the Achilles heel of the diesel king. To maintain its reign, it has had to don increasingly heavy, expensive, and delicate armor. Each new regulation is a siege on its walls, forcing it to evolve in ways that, although successful, take it further away from its simple and robust essence. This weakness is the crack through which its new rivals are trying to slip, promising to comply with the rules of the future without the need for so much chemical alchemy in the exhaust pipe. The rise of electric cars, power without cylinders. The most radical and promising challenger arrives without the sound of explosions. The electric truck represents not an evolution, but a fundamental revolution. Its proposal is as simple as it is disruptive: completely eliminate the combustion process. Instead, massive battery packs power electric motors that deliver all their torque, instantaneously and overwhelmingly, from zero revolutions. It is as if they captured the essence of diesel torque, its immediate availability, and purified it without vibrations, without noise, and most importantly, without local exhaust emissions. For urban and regional distribution applications, its case is formidable. Routes are predictable, allowing for precise load planning. Fuel costs per kilometer are a fraction of those for diesel, Maintenance is drastically reduced. No oil changes, no fuel or air filters, no complex exhaust systems. The mechanical simplicity is overwhelming. Manufacturers such as Tesla, Volvo, Daimler, and a plethora of startups have unveiled prototypes and production models that promise ranges of up to 500 kilometers, enough for many day trips. However, when we look to the sacred realm of diesel, 40-ton long-haul transport, the electric challenge runs into monumental physical barriers. The energy density provided by a diesel tank is, for now, unattainable for batteries of reasonable weight and volume. To match the range of a diesel truck, you would need a battery so heavy that it would steal a crucial part of the payload, negating the economics of the trip. Recharging times, even with ultra-fast charging, are measured in hours, not minutes like filling a tank. And the infrastructure needed to simultaneously recharge dozens of trucks at a service area is comparable to the electricity demand of a small town. The initial acquisition cost remains prohibitively high. Therefore, electric is not a direct replacement, but a disruptor that is creating a new parallel realm, mainly in short and medium-range transport, pushing diesel to retreat and consolidate in its natural stronghold, the open, endless highway. The other contenders, natural gas and hydrogen. At this crossroads, diesel is also seeing the arrival of other contenders that, like it, maintain the philosophy of refueling quickly and moving on, but promise a cleaner profile. The first is natural gas, either compressed or liquefied. Its advantages are clear: significantly lower particulate and NOx emissions than diesel, and a cost per unit of energy that can be very competitive. The engine technology is similar, derived from diesel blocks, which gives it a certain familiarity. But its disadvantages are limiting. Its energy density is even worse than that of gasoline, requiring huge, heavy and bulky tanks that again steal payload. Refueling infrastructure is scarce outside of very specific routes. And although it is cleaner, it is still a fossil fuel that emits CO2. It is a niche player, ideal for captive fleets with fixed routes and their own refueling bases, such as garbage trucks or distribution trucks in ports, but not a generalist contender. The other major contender, shrouded in an aura of promise for the future, is hydrogen. Here, two paths are proposed. The hydrogen fuel cell, which generates electricity on board to power electric motors, offering the electric experience, zero emissions, instant torque, with the advantage of fast refueling and long ranges. And the combustion of hydrogen in adapted engines, an option that maintains traditional mechanics but burns a fuel that only produces water vapor. The potential is immense. However, the shadows over this future are long. The production of green hydrogen through electrolysis using renewable energies is still very expensive and small-scale. The transport, storage, and refueling infrastructure is almost non-existent. The costs of fuel cell trucks are astronomical. And the overall efficiency of the process, from the power plant to the wheel, is lower than that of a battery-powered electric vehicle. Hydrogen is the great promise, the dream of a future without compromise, but its horizon for mass adoption in heavy transport is measured in decades, not years. The farewell is not for today, why diesel remains on the throne. Given this landscape of promising electric vehicles, dreamy hydrogen and limited natural gas, one might wonder if we are witnessing the immediate decline of diesel. The cold, technical answer is a resounding no. For one simple reason: for the specific, monumental and economic task that defines the core of global freight transport, there is no alternative today, nor will there be in the next decade, that offers the complete package. Diesel continues to offer the unbeatable combination of extreme energy density, universal infrastructure, manageable acquisition cost, predictable total cost of ownership, and proven robustness over billions of miles. While an electric truck struggles to exceed 500 miles on a full charge without breaking the bank, a diesel truck does so without batting an eye and can refuel anywhere on a continent in 5 minutes. While hydrogen desperately seeks a network of stations, diesel already has one at every highway exit. Its reign is being redefined, not ending. It is contracting from the edges, from urban distribution, where electric is advancing, but it is growing stronger and more efficient and cleaner at its heart. Long distance. The latest generation of diesel engines are more impressive works of engineering than ever before, with nanometric precision injection systems, composite turbos and intelligent thermal management that approach 50% thermal efficiency, a dream for any combustion engine. They will remain the backbone of the global economy for many years to come. Their demise is not on the agenda at present. What we are seeing is the fragmentation of the future, a mosaic where electric vehicles will dominate the city, diesel will continue to reign on the highway, and natural gas and hydrogen will capture specific niches. Diesel is no longer the sole king of a unified kingdom, but it remains the emperor of the most vast and critical territory. The one where physics, economics, and logistics come together to demand the impossible, day after day, mile after mile. So, the next time you see a truck roaring down the highway, remember that its choice of fuel is not a whim or a simple savings at the pump. It is the endpoint of a century-old equation, carved by the physics of compression, forged on the anvil of durability, and refined by the relentless arithmetic of costs. Diesel didn't win because it was the cheapest, but because it was the most capable for the toughest job. Its history is a testament to how engineering responds to brutal demands with elegant and robust solutions. And while the future brings new challenges, the lesson remains. In the world of heavy duty, the throne is only occupied by those who can move the world again and again without faltering. The journey continues, and diesel, for now, remains at the wheel.